start this. All right. So we are ready to rumble here. We don't really have time to do much of a review. We'll talk more about inverse functions, which is what we started last day. We finished up 1.4 with function compositions, and then we got into inverse functions, and because this is all review anyways, let's just keep going with inverse functions. So specifically logarithmic functions, which are inverses of exponential functions. So today we will finish chapter 1 and just nudge into chapter 2 a little bit. We're going to look at just the slope of the tangent line. If you've done calculus before at some point, you probably remember limits, and that's where we're headed to next. No one likes limits, and that's okay. You still have to do them. So, okay. We're going to talk about logarithmic functions, even though when I write it, it gets smushed. So log functions, if we've got some exponential function with, so if b is greater than 0, and as long as b is not equal to 1, remember if you had b to the power of x, right? If b is just greater, well, b has to be greater than 0. If it's less than 1, right, we've got this decay. If it's equal to 1, we've got this constant function, and if it's greater than 1, then we have this growth curve, right? And so as long as we have one of those, not the constant one, right, so either decay or growth is what we're saying here, then the exponential function f of x equals b to the power of x is either increasing or decreasing, right? Because we said we either have decay or growth. So is either increasing or decreasing. And so it will be 1-to-1 by the horizontal line test, right? And we talked about increasing and decreasing last day. Essentially, a decreasing function, right, is always if you have two x's, right, one less than the other, then the output of the first one is going to be higher than the second one, right? So that makes it decreasing. And so to be 1-to-1, right, is important because in order to have an inverse, the function has to be 1-to-1, right? And so we can check by the horizontal line test. And I don't know about you guys, you probably have it under control, but for me, horizontal and vertical were always kind of like, I don't know. But then I think about the horizon, and the horizon goes like this. So that's the horizontal line test. And so if you can slice it like this and only hit one point on the curve, right, then you can say it's 1-to-1 and therefore invertible. Okay? And so it is 1-to-1 by the horizontal line test. Horizontal line test, which I will abbreviate HLT just in case we need it again. Therefore, right, we said it has an inverse function. Therefore, it has an inverse function called the logarithmic function. Ta-da. Called the logarithmic function with base b, right? So with base b, the same base as the exponential function, And it'll be denoted by log base b. So, oops, that was not supposed to be a b. So just as a rule, log base b of x, if it's equal to y, well, that's the same as saying that b to the power of y is x. So I guess we can put a little, because that's a rule. Some more rules. Just as a fact, if you take the log base b of b to the power of x, it's just going to be equal to x for every x in the set of real numbers. Right. The set of real numbers, remember, is just all the numbers that we can think of. Right. And b to the power of log base b. Notice that these are all the same bases. Base b of x is also equal to x for every x greater than 0. So we'll see later how this is going to help us bring that x down, right? Because it's in the power or it's inside the log, and how do we shake it out, right? And so these are going to be the building blocks towards solving for x, right? The domain of a logarithmic function, or I'll just say logarithmic functions, not just one, but all of them, of logarithmic functions is 0 to infinity. And what does this mean? This means that we can't take the log of a negative number, right? We can't even take the log of 0 because 0 is not even included, right? And so we can't take the log of 0 or a negative. Which means that we have to add that to our toolkit, right? When we're checking for the domain, we used to just have to look for, well, I can't take the square root of a negative number and I can't divide by 0. Now we have to add the third one that we have to, so taking a log has to be greater than 0, right? Not including 0. And so now we've got 3 things that we're on the lookout for illegal math, right? And so and then the range of a log function is the set of real numbers. And so in general, log base b of x looks like, oops, looks like this. And just like the exponential functions pass through 0, 1, right? All these log functions, regardless of the base, they're all going to pass through 1, 0. So all of these log functions are going to pass through 1, 0, meaning that when x is 1, right, that's when the output is going to be 0. We have to establish the laws of logarithms. So we'll just list them here. Laws of logarithms. I should probably stop spelling it out, but I always logarithms. If x and y are positive numbers, right, which is just to ensure that we're able to take the log of these things, right, it has to be a positive number, then the first rule, or the first law, is that the log base b of x times y can be rewritten as the log base b of x plus the log base b of y. It does assume that you have the same base, right? Otherwise you can't combine them. But if you've got log base b of x and then log base b of y, usually what we want to do is we want to simplify these things, and so we smush them together into just the one log base b of x times y, right? So if you're adding on kind of separate logs, then you can combine them and multiply the insides. 2, kind of same idea, log base b of x over y is the same as log base b of x minus log base b of y. Okay. And that comes from the last law, or the last one that we're going to focus on. Log base b of x to the power of r can be rewritten as r times log base b of x, and I'll just say where r is any real number is in the set of reals. Okay. I'll put a box around these laws here. This last one, that's our moneymaker, right? Because if we've got something in the power, right? If we take the log of it, right? So if you're just looking at x to the power of r and you're solving for r, right? Then, and you want to bring this down, then we can wrap it up in a log, because by this property, right, then we can rewrite this as r, right, just bringing that power down in front, r times the log of x, right? And so that's going to be kind of the most important thing that we can do. And also, it explains how this guy came from this one, right? Because we could rewrite this as x times y to the power of -1, right? If we brought this y up top. And then we would have this property, right? The log of x plus the log of y to the -1, right? But then that -1 by this property, we can bring it down in front. And so these are all codependent, right? And so they all hinge on each other, right? But that explains why if we're dividing, right, then we've actually got that negative power, which we're bringing down in front. And so they're definitely related. Okay. Any questions about that? I love working with logs, simplifying logs. I think it's so fun. But anyways, so maybe that's just me. As a little example, use the laws of logs, which I like, log laws, right? Fun to say, fun to do. So the law of logs, or log laws, to evaluate something like log base 2 of 80 minus the log base 2 of 5. Let's give it a quick go. So I'll start this here. We've got the log base 2 of 80 minus the log base 2 of 5. Well, I can rewrite that because I've got log base 2 and log base 2, so I'm allowed to squish those together. I'm subtracting, so I know I'm going to have log base 2 of 80 over 5, right? And so log base 2 of 80 divided by 5. 80 divided by 5 is 16, so now I have log base 2 of 16. Here's the tricky part, right? You'll want to check out your calculator. It might just let you tell it what base you want, but if it just says log, it's log base 10, right? And so that's not what we want. Or if it says ln, right, that's log base e, which we'll get into. This calculator has the option of putting in any base, right? We don't actually need that option. I'll show you guys later the trick using the ln button for the change of base. But for now, we just need to say, okay, well, this is equal to 4, right? And the reason for that is since 2 to the power of 4 is 16, right? So I want you to think, oops, missed a line. Think 2 to the power of what is 16? Well, 2 to the power of 4 is 16. I personally never liked these types of problems because so what? I'm just supposed to realize that I'm supposed to think of 2 to the power of something equals 16. And so I like the concrete stuff. And we will be able to solve this without having to pull random numbers out of the air and probably testing them, right? Especially if it's not something that we're familiar with, right? 2 to the power of 4, you probably would have landed on it pretty quickly, right? But usually that's not the case, right? And so I'll show you guys how to evaluate something, so any log base, right? Just using the default functions on your calculator. Right? We'll still need our calculator, but not bad. So let's talk about natural logarithms. Natural logarithms. So all the laws that we established, right, base B, they apply to all the logs, right, or all the log laws are for all the logs. Wow. But what we'll find is that often the most convenient base is going to be E, right? E is just a constant. Keeps going forever and ever, but it's still just a constant, right? And we talked briefly about E, right? Because the slope of the tangent line at what was it? 1, 1, 1 was 1, something like that. Can't remember exactly. We'll get there. We'll review it. So often the most convenient base for a log, oops, is E. Log base E of x, we just write as ln x. And this is called the natural logarithm. Oops. Just a heads up, when I write it, usually it ends up looking like this, just so you know, right? So when I write ln, I don't usually spend a lot of time. I just do a little ln kind of cursive scribble. And another heads up is that, and this is true for a lot of fields, log base e is the only log that we ever use in stats, for example, right? So upper level statistics, you're just going to use log base e. There are no other logs that we care about. And so I got into the very bad habit of calling ln just the log, right? And that's for my prof, so that's the log, ln. So I try to call it the natural log, but sometimes I'll slip up, and when I say log, I'll probably mean the natural log. So I apologize, and I try to stay on top of that, but it's tough. Old habits die hard. So we're also going to note that log base 10 of x, right? And we kind of mentioned this, is just going to be written as the log of x, right? So we kind of drop the 10, and this is called the common logarithm. So if it's base e or if it's base 10, then we've got these kind of default notations. Any other base, yeah, we have to specify, of course. We're not going to work a whole ton in log base 10, but log base 10, I think it's for like frequencies. So obviously not a lot happening, but like sound frequencies, things like that. So they work in log base 10, but pretty much every other field works in log base e. So, all right. So the natural log. We've got the common log, but we're going to talk about the natural log. So we know that if the log of x, sorry, the natural log of x, that was too soon. I shouldn't have said that. I should have caught that already. If the natural log of x is y, well, that's the same as saying e to the power of y is equal to x. All right, so these two are equivalent. So we'll kind of keep that in mind. That's the exact same as what we just said at the very start of our notes, right? We said, well, if the log base b of x is equal to y, right, then b to the power of y is equal to x. This is just the specific base b of e, right? Oh, so many letters. Some mean numbers, some mean just variables. Thanks. And just applying those same rules that we covered in general at the beginning, right? Then the natural log of e to the x is just x, as long as x is in the set of real numbers. I'll clean up here. And then e to the natural log of x is also x, as long as x is greater than 0. Right? So this is how we're going to cancel a natural log or e, right? If we just have e to the x and we want to solve for x, then we would have to take the natural log of it, and then that portion will disappear and we're just left with x, right? What we do to one side, we have to do to the other, of course. So it can make a little bit of a mess, right? But that's why we need the log laws, so we're able to simplify our logs. And then if we have the natural log of x, right, to dissolve the natural log, we have to take e to the power of both sides, right, to get that x down. And of course, letting x equal to 1 is the same as taking the natural log of e, which is also equal to 1, right? So these are all equivalent. So the natural log of just e to the power of 1 is just 1, right? So, all right. Let's do an example. So if we have to solve, and I'll give you guys a little bit of time to do this, to work on it. The first one, the natural log of x is equal to 5, right? Of course, if I say solve, I mean solve for x. B, e to the power of 5 minus 3x equals 10. And C, the natural log of x minus 2 plus the natural log of x equals the natural log of 5. Especially for that last one, I want you to pay attention to the domain, right? Meaning there will be values of x that just are no-goes. So give you guys a little bit of time to work on this. And then we'll go through it. questions, I'm pretty sure you've got part A under control. I'll start there and have a little bit more time to work on that last one, so it's a little bit trickier. So if we've got the natural log of x equal to 5, right, what we said earlier was, well, if I want to shake out the x out of a natural log, I'm going to have to take e to the power of both sides, though, right? And so what I'm going to have to do is I'm going to have to take e to the power of the natural log of x is e to the power of 5. E to the natural log of x is just going to reduce to x equals e to the power of 5. And whether you wanted to evaluate that, I would probably just leave it as the exact answer, right? E to the power of 5 is exact. Or if you want to approximate it, e to the power of 5 is x is approximately 148.41311591. Yeah. For part B, we had the e to the power of 5 minus 3x equals 10. Again, my x is kind of wrapped up first in a natural log, now in an e. Either way, right, to undo the other, right, we have to wrap up the e in an ln, right? And so we can take the natural log of e to the power of 5 minus 3x, and then remembering to take the natural log of the other side as well, right? The natural log of 10, right, is just some number. So we can just treat it as a number. Technically, right, if we take the log or the natural log of e to the power of 5 minus 3x, what we get is 5 minus 3x times the natural log of e, but the natural log of e is 1, and so it'll dissolve. And so what we get is 5 minus 3x, right, by that very handy rule that if we take the natural log or any log of something with a power, the power can be brought down in front. And so 5 minus 3x times the natural log of e is equal to the natural log of 10. Just make a note here, the natural log of e is just 1, so it'll just go away. So now we've got 5 minus 3x. Oh, I guess I can ditch those brackets. Is the natural log of 10. Clean that up. Treating the natural log of 10 as just a number, right, which it is, we can solve for x. If I do 5 minus the natural log of 10 is 3x, then I have x is 5 minus the natural log of 10 over 3. Doing that switcheroo, kind of that revolving door around the equal sign, because I like to have whatever I'm solving for on the left-hand side. Okay, and that's it. You can evaluate that if you want to, but this would be the exact answer, right? If you took 5 minus, and then any scientific calculator should have an ln button. The ln of 10, it's just a matter of finding it, and then divided by 3, well, x is approximately equal to 0.89913833023. All right. Last one was a little bit tricky, right? We said, okay, well, we're going to solve the natural log of x minus 2 plus the natural log of x is equal to the natural log of 5. Pretty sure that was it. So first, we can use the log laws to combine the logs on the left-hand side. And so what we have, right, is we're adding two logs of the same base. And so we've got ln of x minus 2 times x, right? We can multiply inside. And I'm going to start writing ln like that because it's too hard. Two separate letters? Man. Oh, thank you. So now we've got the natural log of x minus 2 times x makes x squared minus 2x, which is equal to the log of 5. Now what's nice is that we've got a natural log on both sides. So when we raise this both sides to the power of e, right, or e to the power of both sides, I guess, we get e to the ln of x squared minus 2x is e to the power of ln of 5. Well, e to the ln just drops whatever is in the ln. And so we get x squared minus 2x is equal to 5. Cool. Trying to solve for x, right? If I move that 5 over to the left-hand side, then I get x squared minus 2x minus 5 is 0. Right? And now you might remember quadratic equation, quadratic formula, right? And so now we've got a quadratic so you might have it committed to memory. You might not. You probably will by the end of this course. But x is negative b plus minus the square root of b squared minus 4ac over 2a. And that's how we find the roots of a quadratic equation. And because it's equal to 0, right, we are finding the roots. So now, having worked with the quadratic equation before, we know we're probably going to get 2 answers. And then because I gave you the heads up of looking at the domain, one of those is probably not going to work, right? So we need to figure out which one's which. But let's solve it first. So we've got negative b, and b is negative 2. So negative 2, bless you, plus minus the square root of negative 2 squared minus 4 times a, which is 1, and c, which is negative 5, over 2 times a, which is 1. So I get 2 plus minus the square root of 4 plus 20 over 2. So I have 2 plus minus the square root of 24 over 2. This will give us the answer, right? But if I want something a little bit nicer to look at, what I can try to do is I can try to factor out a 2 from that square root of 2 of 24, right? And so, well, to get a 2 out of a square root, right, I have to take the square root of 4. And so I'm going to try to pull out a factor of 4 from the 24, which leaves me with 4 times 6, right? And so what I get is I get 2 plus minus the square root of 4 times 6 over 2. Because I'm multiplying inside that square root, that's what lets me pull out the root 4 times root 6. So I get 2 plus minus the square root of 4 times the square root of 6 over 2, showing a lot of steps here, right? But I want you to see where I'm coming from. And then I get 2 plus minus 2 root 6 over 2. Now, because I have a 2 on both sides of the plus minus, right, I'm allowed to cancel that 2 in the denominator. And so now I get 1 plus minus 1 times root 6. So it's either going to be 1 plus root 6 or 1 minus root 6. Both of those are solutions, right? So now we need to consider the domain of the function to determine if one or both or none of these solutions are going to work. We need to consider the domain of the function to determine which, if any, solution solves the equation. So remember, we had the natural log of x minus 2 plus the natural log of x. Sorry, I'll change this one actually. Can't keep that up. Is the natural log of 5. We said for any log, right, x has to be a positive value, so it can't even be 0, right? It has to be greater than 0. And so what we're going to say here is, well, for this little guy here, right, then I know that x minus 2 has to be greater than 0. So my restriction here is that x must be greater than 2. And then for this portion, I've got just x, and I know that x has to be greater than 0. Combining these two, if x has to be greater than 2, but also greater than 0, well, we can just summarize that by saying, well, x has to be greater than 2. And so therefore, x must be greater than 2. If our solutions were that x is 1 plus root 6 and x equals 1 minus root 6, I'm going to go ahead and say that 1 minus root 6 is going to be less than 2, right? And so that's no bueno. So 1 plus root 6, we'll just make sure, right? And you can use your calculator. 1 plus the square root, the square root of 6 is roughly 3.449. Right? So that's allowed, so that is the solution, right? So here, I've got a page break, so I am going to go across the page here, but this is approximately 3.449. So I'll use this color. This is a solution. Okay. 1 minus the square root of 6 is roughly negative 1.449, right? So that means it's not a solution. So even though we were able to find 2 answers, right, these 2 answers aren't going to lead us to 2 solutions. So there's only 1 solution. Right? So you want to be a little bit careful. Any questions about that? Oh, yeah.
We answer rate, so make sure that rate is wrong.
No, I'm just emphasizing why why that is. But you do have to tell me the reason one would be a solution, right? Because x is greater than 2, or x has to be greater than 2. But no, you don't have to show both solutions. You could just say, so 1 plus root 6 is the solution. Right? That's fine. So how about if you have to express the natural log of a plus 1/2 the natural log of b as a single log, as a single logarithm. Let you give that a go. Right. Using those log laws. So if you're looking at this, right, you know you can, so if you're adding logs at the same base, then you know you can squish those two together inside, right? But it's the 1/2 that's probably holding you up. So what you can do is you can say, okay, well, the log actually brought that 1/2 down, so I could just as well rewrite it with the 1/2 in the power of b, right? So we can rewrite this as the natural log of a plus the natural log of b to the power of 1/2, right? Because those two are going to be equivalent. And so now we're free and easy with these logs, and we can combine them because we're adding them, and so we can combine them to a single natural log of a times b to the 1/2. B to the 1/2 is the square root of b, which is a little bit nicer to look at, right? And so we can have the natural log of a root b, although the previous answer is also, that's done, right? Just like to write it as a square root. We can. And there you have it, single log. So now that we've talked about the natural log, right, now I can show you the easiest way to calculate any log base using your calculator, even any scientific calculator, right? Because any scientific calculator will have the ln button. And so to calculate the log base b of x of any base b, we can use the change of base formula. And I'll just put in brackets to explain, as all scientific calculators will have an ln button. As all scientific calculators will have an ln button. So the change of base formula just says that, okay, well, for any positive, right, we have to be able to take the log of it. So for any positive number b, as long as b is not equal to 1, we have, I guess it was referring to the base. Anyways, we still have to take the log of positive numbers. We have that the log base b of x, we can rewrite that as the natural log of x divided by the natural log of b. So this one's going to be really handy depending on, you know, what kind of calculator you're working with. And for this course, it can be any non-programmable calculator. Right? So probably scientific, right? You don't want to have one of those little quick desk ones. I have seen people show up to stats exams with that, and I'm like, what are you planning on doing here? It's gonna take you forever. But anyways, so scientific, but that's about the only restriction. So if we want the log base b of x, right, we take the natural log of x over the natural log of b, and then we get the same answer. So just, oops. Just as an example, if we have to evaluate log base 8 of 5, correct, to 6 decimal places. If we have log base 8 of 5, well, we can rewrite that as the natural log of 5 over the natural log of 8. That is the exact answer, but in this case, right, we want the decimal approximation to 6 decimal places. So if you take the natural log of 5 divided by the natural log of 8, I get roughly 0.773976. 3976. 1, 2, 3, 4, 5, 6. Nice. So this, the change of base formula, right? That's how we would go back and actually solve the problem that we started with, where we said, oh, I have to think of 2 to the power of what equals 16, right? I don't like those types of problems. So for me, I would probably just go to the change of base formula, right? And because, well, I've got it here. What were we trying to solve? Log base 2 of something, I think. Log base 2 of 16, right? So log base 2 of 16, well, that's the natural log of 16 over the natural log of 2. You give it a go. The natural log of 16 divided by the natural log of 2 gives us 4, which was the answer we landed on, right? 2 to the power of 4 is 16. But I just way prefer to have these kind of hard rules that we can follow, right, for these log of any base problems. Any questions before we get into inverse trig? We'll get in and get out and use it as needed. Yeah. All right, so inverse trigonometric functions. Remember when we said, okay, well, in order to have an inverse, right, a function has to be one-to-one, but we know what sine and cosine, right, are kind of two go-to trig functions, and even tan, right, even though it's kind of nasty with all those asymptotes, right, we still know what all those look like. And if we draw a horizontal line, there's no way that we're going to only touch one point in the curve, right? We're going to keep touching it, keep touching it, keep touching it. And so, but we also know we know that there are inverse trig functions, right? You've probably seen them at some point. And so to find those, what we do is we say, well, what if we only look at this little window, right, of sine, for example, right? If we focus on the sine curve between negative pi over 2 and pi over 2, then we'll have a one-to-one function, right? Because I guess it'll just be the little blip, right, where it's one-to-one. So when we try to find the inverse trig functions, we encounter a problem. You might remember, and you probably do remember, but you might remember that sine of x, that sine of x, cos of x, and tan of x are not one-to-one. Right. As is easily seen using the horizontal line test. Oops, the HLT, I'm calling it. Right. Because we know that, well, they're not going to be one-to-one. I can hit that curve an infinite number of times. And so to overcome this, we restrict the domain. So to overcome this, we restrict the domains until the function becomes one-to-one. Right? So we only look at a little portion, as much of the curve as we can, right? But just until it's one-to-one. Right? And so we restrict the domains until the function becomes one-to-one. So what we said was, okay, well, f of x equals sine x is not one-to-one. But f of x equals sine x, as long as x is between negative pi over 2 and pi over 2, is one-to-one. Right. So with that restriction on there, it is one-to-one. And so this restricted function, that we can take the inverse of. right? And so that's the inverse function that we are familiar with, right? The one on our calculator that we've been using probably without really knowing why. So this is why. The inverse function of this restricted sine curve, of this restricted sine function, I'll call it, exists and is denoted by sine, the inverse sine, or arc sine. We'll use those two interchangeably. So you could do the sine and then to the power of -1 to follow the same format as all our other inverses. Or we can also call it arc sine, and it's just up to you to remember that those are the same things. And so applying that same idea, right, that same method to cos and tan, we can find the inverses of those as well. And so we apply the same methodology to find the inverse cosine, to find the inverse cosine, which we're going to denote much in the same way, cos to the -1 or arc cos. And the inverse tangent function, same thing, tan to the -1 or arctan. Usually it ends up being a matter of what's easier to write, what sounds better, right? So we use these interchangeably. What looks better. And so the inverse sine is going to look something like this. So it goes between -1 and 1. And it only goes, so it has a range between -pi/2 and pi/2. I'll scoot the pi/2 down a bit, I think. So the inverse sine has a domain from -1 to 1 inclusive, right? So square brackets, and range. Remember the inverse of a function, right? The domain of the original function becomes the range of the inverse function, and then the domain of the inverse becomes the range of the original function, right? So if the domain that we've restricted our sine curve to is from -pi/2 to pi/2, then now the range for our inverse sine is from -pi/2 to pi/2. Right? And then we know our original function sine, right, had a range from -1 to 1, and so that's becoming our domain of the sine curve. Right? So they're related. So what are these going to look like? Well, these are going to look like here it passes through -1, -pi/2, and ending up at 1 pi/2, and it just kind of has this tangent looking shape, right? But that's all of it, right? And so these are closed dots. the inverse cos, right? Again, let's sketch it out to have a look. The inverse cos is going to have a domain from -1 to 1, right? Because it has the same range as sine, right? Cosine and sine have the same range. And so now the domains of these are going to be the same for the inverse, but the range, the way that we've restricted it is from it's from 0 to pi. I wanted to say it for sine again. From 0 to pi. So what it's going to look like is here at 1 and going to -1, it goes from 0 to pi, and I'll put pi here, and it's going to pass through at pi over 2, just as a rule. And how does it look? It's going to have the same shape, but I didn't draw it very well. Right. But it's going to pass through pi over 2 on the y-axis, and it's going to end at 1, or x equals 1. And it has these closed dots there. The only one of these that's kind of interesting is the inverse tan, right? And so if we're looking at the inverse tan, what it's going to look like, and I'm going to need one more line there. The range of the tangent function, right? That's the one that goes like, brr, 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 right? And so the range of the tangent function is the set of real numbers, right? Just keeps going and going and going, right? You've got those asymptotes, but it just keeps going. So now what's interesting about the inverse tan is that it's going to have a domain of all the real numbers, right? Which is different from the domain of the inverse sine and cosine, where you're just stuck between -1 and 1. Right? And so, and the range, right? The range is going to be restricted by the domain of the tangent function, which is going to be between -pi over 2 and pi over 2, not inclusive. And so -pi over 2, because that's where our asymptotes are, -pi over 2 and pi over 2. So what that's going to look like is here at pi over 2 and -pi over 2. Oops. I've got these horizontal asymptotes, which I'll just kind of box myself in with these dotted lines. And then what it's going to look like is it's just going to start down here and curve up and kind of curve off that way. Having a domain of the set of real numbers, right, is what makes the inverse tan the most interesting one to look at. And so of all the inverse trig functions, that's probably the one that we're going to come back to, right, because it has this more interesting shape. Yeah. But that's all we're going to say about inverse trig for now. Any questions? No. Okay. Where's my page break? Here. Sure. New chapter, new page. So that's the end of chapter 1. Right. Hopefully you've started assignment 1 already, right? Because it's due on Sunday at midnight. Right? And so assignment 1 is just on all the chapter 1 stuff. And it's just applying all these things, right? So we talked about all these concepts. Now it's time to apply them. If you're working in, well, you will be working in WebAssign, right? And so how it works is if you get the question right on the first try, then that's great. If you get it wrong, then the next time you try it, there'll be options for you to kind of read more about this problem, try a similar problem. Sometimes there's even videos of, say, of them solving a similar problem, right? And so, but if you get it right the first time, then I don't think you get those resources right away. They kind of, I don't know why, but they kind of hold back. I think it's so that you can see if you actually got it or if it was with a crutch. But either way, I think those are really good resources, right? And so especially read more about this. It'll take you to that spot in the textbook where that material was covered, right? And then you can kind of read more kind of detailed. So chapter 2, this is where we get into not necessarily review stuff, right? Some of it might be review depending on how far you've gone. What's tricky with this course is a lot of people have, taken calculus in high school and just kind of taken a little bit of calculus at some point. So I don't know where everyone's at, but that's not necessarily true, right? I think you just need math 11, 12, something like that. So not necessarily having done calculus. All right. 2.1. We're just going to start talking about the tangent and then applying it to the velocity problems. So the tangent and velocity problems. So tangent is derived from the Latin word touching. And so a tangent line, right, is a line that touches a curve, but only at one point, right? And then the key thing is that it has to have the same curve. So curve at point B, right? We're gonna have to, and then easier with don't have anymore, right? but if so we have to. And so the tangent line, right, and the special slope of the tangent line is going to tell us a lot about what's happening on the curve at that specific point. Right? And so the tangent line to a curve is a line that touches the curve at only one point. Is a line that touches the curve at only one point. And has the same direction as the curve. So that's going to be key, right? And has the same direction as the curve. And has the same direction as the curve at the point of contact, at the point of contact. Just to kind of emphasize, right? If you've got a curve and it looks something like this, and I want to find, right, what's going on at this point here, you would probably put the tangent line, right, just kind of like this. It would look something like this. That wasn't very good. It's a little bit lifted, but right. That's if it has the same direction. The reason we have to specify that it has to have the same direction, right? I'm going to redo it actually. I just didn't like how that went. There, a little bit better. That has the same direction as the actual curve, right? Technically, you could have drawn something like this. Yeah, that only touches the curve at one point, but it doesn't tell you anything about what's going on at that point, right? So that's not the one that we're going to use. And so the tangent line just touches, and then we're out of there, right? But because it's a line, it's going to have a slope, and so that's going to tell us about the behavior at that point. And so what we're going to end up doing is, well, we can't find the slope at a single point, right? Remember, the slope is rise over run, so we need to have a starting point and an end point. And so what we're going to start by doing is we're instead going to look at the secant line. Secants, I think, is Latin for cutting. I don't know, it's in the textbook. I'm not. What is it when you study words? Etymologist? Something like that? I don't know. Anyways, I like it, but I don't know it. So anyways, so secant is, the secant line is, it's going to cut through the curve at 2 points. But what we're going to do is we're going to move that second point closer and closer and closer to the point that we're actually interested in, right? And that's where we're going to get our limits from, right? The limit as we approach this point, right? And so that's where we're headed. Example 1 that we're going to work through together is just, okay, well, find an equation of the tangent line to the parabola, right? Just starting off small, something that we know what it looks like, y equals x squared, at the point P, which is going to be at 1, 1, right? Are you guys familiar with that kind of point notation, right? So we're going to call that point P, and that's at 1, 1, and that's on the curve, right? Because if x is 1, right, then x squared is going to be 1 squared, which is also 1, right? So it is on that curve. Okay. So if we want to find an equation of the tangent line, right, y equals mx plus b, well, if we've got a point, we can use the point slope form, right? But that means we need to find the slope first, right? So first we need to figure out what the slope is at that point, and then we can figure out the equation of the tangent line. And so we need to first find the slope of the tangent line but we need a second point in order to do that. But we need a second point in order to do that. So what we're going to do is we choose a second point Q, which can be any point of x as long as it's on the curve x squared. So we just denote it by q x squared. But we're going to choose it near P11, right? We're interested in what's going on at 1, 1, so there's no point in picking x equals 100 because, well, we don't really care what happens at between 1 and 100, right? We want to get close to 1. Right? And so we choose a second point, Q, near 1, 1. By showing Q as x squared. We know it's on the parabola, but on the parabola. And the goal is to compute the slope of the secant line. The slope of the secant line which we will denote by m, right? Mx plus b, y equals mx plus b, right? M is usually used for the slope. And so m subscript p subscript q. M is the slope of the line connecting P and Q. Slope of the line connecting P and Q. And PQ. So what we're going to have, right, is something like this. If we've got x squared, something like this. Here's 1, 1. Then what I'm going to do is I'm going to find, I should have zoomed in a little bit. That's not very good, is it? Oops. Make this kind of lofty x squared here. Look weird on this side. So here I would let Q be x squared. And then what we're going to do is we're going to move Q closer and closer to P, right, as close as we can. We could also, my default is to start above and work my way down, right? But we could just as easily work our way from 0 and get closer and closer to 1. Right? Either way works. So we know that the slope between P and Q is rise over run. And so if we're looking at this diagram here, our rise would be between x squared and 1, right? X squared minus 1. And my run is going to be x minus 1. Rise over run. So a nice point of Q might be at x equals 1.5, right? 1.5. We can plug that in. 1.5 squared puts us at 2.25, right? And so now we're at 1.5 and 2.25. And so letting Q be at 1.5 and 2.25, we find that the slope, MPQ, is 2.25, right? Because that's x squared if x is 1.5. 2.25 minus 1 over 1.5 minus 1, which is 1.25 over 0.5, which is 2.5. So between x equals 1 and x equals 1.5 on the parabola x squared, right, the slope is 2.5. So it's increasing at a rate of 2.5. So now what we can do is usually we just set up a table of values and just move down closer and closer to x equals 1, right, kind of incrementally. And so we could also find, I'm just going to give them to you. Right, if we have x is 2, 1.5, 1.1, 1.01, 1.001, so 2 zeros, sorry. I can find MPQ. I'm just going to give them to you, but you would find them the same way. If you have x equals 2, that's actually further away, and so it has a slope of 3. We just did 1.5, and so we know that the slope here is 2.5. And then at 1.1, if we did it, it would be 2.1, and then 2.01, and then 2.001. It's really looking like as we get closer and closer and closer to 1, right, our slope is going to be 2. Right? But let's just make sure by checking from the other direction, right? And so, and I'll just give them to you again. And if x is 0, 0.5, 0.9, 0.99, right, getting closer and closer to 1 from the other end, 0.999, we get MPQ again of 1, 1.5, 1.9, all of a sudden closer to 2 again, 1.99, and 1.999. So regardless of the direction that we're coming from, right, the slope appears to approach 2. So as we let Q approach P or go towards P or whatever you want to say, right? Usually I'll say approach. As Q goes to P, or I guess goes to, got lots of options. As Q approaches P or goes to P, we see that the slope between P and Q is moving towards 2. So what we're actually saying here, right, is that the slope of the tangent line is the limit of the slope of the secant lines. And so we say that the slope of the tangent line is the limit of the slopes of the secant lines. And we denote that by saying the limit, so LIM, and then usually underneath the limit, we say as Q approaches P, right? So the limit as Q approaches P, or as Q goes to P, and then we put of what we're taking the limit, right? And so of MPQ is just M, right? The slope of the tangent line. Just as a heads up, because we will be writing LIM a lot, and so it looks a lot like my LN, but there's a dot over. I know, but, well, that one was really not nice. Worst case scenario, I guess, there, is usually how I'll write my limits, right? You'll know because it'll have the limit of Q, so the limit as Q approaches P of MPQ. So you'll know it's a limit just by circumstances. And so what we found, that the limit as P approaches Q, right? Sorry, I'm not doing the general one anymore. I'm doing for our problem. So the limit, what we were changing was the Q, but specifically the X in the Q, right? And so the limit as X approaches 1, right, as we moved X closer and closer to 1, and the function we were looking at was X squared minus 1 over X minus 1. The limit of this, we decided, is probably 2. So we found the limit. It's possible that that's wrong, right? But as far as we know, right, we checked both sides. There's no reason to think that there's a big kind of jump going on there or anything like that, right? And so from here, we can say, okay, well, assuming that the slope of the tangent line is 2, right, then we can use the point slope form, because remember the goal was to find the equation of the tangent line, right? Y equals mx plus b. And so here, assuming the slope of the tangent line is 2, right? So m equals 2, we can use the point slope form of a line to find the equation of the tangent line. To find the equation of the tangent line. Point slope form, y minus y1 is m times x minus x1, right? Where the point is x1, y1, that you know, and you need to know the slope as well. So we know the point that it's passing through is 1, 1. We know the slope, we're saying, okay, we're gonna assume it's 2, just straight 2. So I can plug these in, so I get y minus 1 is 2 times x minus 1. Solving for y, right, moving that minus 1 over, I get y is 2x minus 2 plus 1. So I get y is 2x minus 1. And that would be the equation of the tangent line. Nice. Last thing, we're going to apply this to a velocity problem. It behaves the exact same way as what we just did, right? We're going to know what the curve of the distance traveled looks like, right? And then if we're looking at it over time, then distance over time, right, gives us the velocity. And so now we're able to zero in on the instantaneous velocity, not just the average velocity, which would be essentially the secant line, right? The average would be the secant line, and then the instantaneous would be the tangent line. Right? And so let's just get into the velocity problem. I'll just write it down. So finding the instantaneous velocity of an object, finding the instantaneous velocity of an object, oops, follows the same structure as the example we just did. Follows the same structure as the example we just did. So I'll put this example on the new page. So example 3, oops, just combining all kinds of things here. Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, obviously from the textbook. And can't remember if James Stewart, did he go to, I think he went, yeah, U of T. Surprise, surprise. But pretty cool. So suppose that a ball is dropped from the upper observation deck, of the CN Tower in Toronto, which is 450 meters above the ground. Oops. Find the velocity of the ball after 5 seconds. So we're going to find the velocity of the ball after 5 seconds. So that's an instantaneous velocity, right? And so we can graph the distance traveled. Now, I guess it does assume that you've done some physics. I'm just going to give you the formula, right? I would never, on a test especially, I would never give you a problem like that and just, yeah, figure it out. No, I would give you the equation for the distance traveled, right? And so, but here I'll say from physics, we know if the distance fallen after t seconds is denoted by S of t, and measured in meters, then we can say that S of t is going to be 4.9 times t squared. So for me, I wouldn't end the problem, just find the velocity after 5 seconds, right? I would end it here instead so that you have everything that you need. And so the same way that we couldn't find the slope of one point, right? It can be anything, right? We also can't find the instantaneous velocity at just one point, right? We can find the average velocity between 2 points very close to each other, and that's what we're about to do, right? And then apply those limits, or the idea, at least the idea of a limit, to solve it. And so we can't compute the velocity at a single time point right, t equals 5, for example, but we can approximate it by finding the average velocity over a brief time interval. Right. Say something like t equals 5 to t equals 5.1 seconds. Right. Something like that. From probably any physics that you've taken, right? The average velocity is the change in position, right? We're talking about the average here because we are going to have to take the average velocity and take the limit of it to find the instantaneous velocity. And so it's the change in the position divided by the change in time, or time elapsed, if we want to get fancy. If our function s of t is the distance, right, then that's the change in position, right, or that's the position, right? And so the change in position in our case would be s at 5.1 minus s at 5. Presumably, I've gone further after 5.1 seconds than I have after 5 seconds, and so that's why I'm doing the distance after 5.1 seconds minus the distance after 5 seconds over, and then between 5.1 and 5 seconds, I've gone 0.1 second. And so I can replace s of 5.1 by 4.9 times 5.1 squared minus 4.9 times 5 squared over 0.1. If I do this on my calculator, I get 5.1 squared. I'm going to start there. Times 4.9. Oops. And this becomes, and I'm going to scoot it over because I've got a new page here. I get 127.449 minus, and then 5 squared times 4.9. 122.5 over 0.1. 127.449 minus 122.5. I get 4.949 over 0.1. I get exactly 49.49, and it's the change in distance, right, which is going to be in meters, over the change in time, which is going to be in seconds, and so my units here are going to be meters per second. So that's between 5.1 and, or 5 and 5.1 seconds, right? And so what we can do, and I'll just give you the values, but we can condense that time interval, right? Move it even closer to 5 seconds. And so if we have a time interval looking between 5 and 6 seconds, right? Our average velocity in meters per second turns out to be 53.9. We wouldn't actually go from 5.1 seconds all the way to 6 seconds. It doesn't, we don't really care about it. But just to show you that things are changing pretty quickly. So then between 5 and 5.1, which is the one we just did, we're gonna get to 49.49. Between 5.05 and 5.05, we get to 49.245. Between 5 and 5.01, getting closer and closer to 5, right, we get 49.049. And then we'll kind of tap out at between 5 and 5.001, puts us at 49.0049. Here, right, if we were just to keep going and going and going, right, it looks like it's going to approach 49. Right? And so therefore, it appears the instantaneous velocity, instantaneous, yikes, velocity at t equals 5 is 49 meters per second. You want to be careful, right? Because between 5 and 5.1, we actually got to 49.49, which is still a little ways off, right? And so you do want to try a couple of more points just to see if things are still changing. Any questions? Cool. For next week, we're going to do, so read sections 2.3, or sorry, 2.2 first. 2.2, 2.3, and 2.5, right? We're not doing 2.4. All right. See you guys later. See ya.